So this research is about alternative ways of storing data, digital data, for archival purposes with DNA.
The initial thought was, I don't care what I'm building, and so why don't we just build Moby Dick or something? I'll just encode it into DNA, and we'll just build that because I don't want to worry about the design at this point in time.
Sri and I debated what we should encode, what would nicely represent the digital universe, and we wanted something that represented sort of modern digital. So we used an HTML version of a book that I wrote recently called Regenesis. The HTML form, let's say the web form, includes images, digital images. It includes JavaScript programming language that actually does perform something interactively with a person. And so we encoded that into zeros and ones and then into DNA.
Welcome back to Digi.AI.Velocity, your ultimate source for all things AI and technology, where we dive deep into the cutting edge of technology. Today, we explore a fascinating breakthrough in data storage that could revolutionize computing forever. We're talking about deoxyribonucleic acid, or DNA data storage. Yes, you heard that right, using the building blocks of life to store our digital world. Let's explore how DNA could be the future of data storage. Let's begin. As the digital world continues to expand, our need for efficient and sustainable data storage has never been more pressing. Traditional methods, like magnetic tapes, hard drives, and SSDs, are reaching their limits. But what if the solution lies in the same molecules that make up our DNA? DNA data storage is exactly what it sounds like, encoding digital information into DNA sequences. DNA is made up of 4 bases: adenine, A, thymine, T, cytosine, C, and guanine, G, and scientists have found a way to map binary data, the ones and zeros of computing, onto these 4 bases. This process allows us to store enormous amounts of data in a molecule as small as a speck of dust. For instance, 1 gram of DNA can store 215 petabytes of data. To put that in perspective, that's around 215 million gigabytes. A single DNA strand can store all the information created by humanity up to this point, and more. So, how exactly does this work? There are 5 key steps. Step 1. Data encoding. First, digital data is converted into binary code. Then, a specially designed algorithm translates this binary code into DNA sequences. Step 2. DNA synthesis. Next, the DNA sequence is physically synthesized in a lab. This DNA is identical to natural DNA but stores digital information. Step 3. Storage. Once synthesized, these DNA strands are stored in tiny containers, often freeze-dried for preservation. DNA is incredibly durable, with the potential to last thousands of years. Step 4. Data retrieval and sequencing. To read the data, scientists use genomic sequencing to decode the DNA back into binary and reconstruct the original file. Step 5. Error correction. Finally, error-correcting algorithms ensure that the retrieved data is accurate, even if small errors are introduced during sequencing.
The book we encoded was actually a book that George has written, and in the book is a section on this particular piece of work. So the sentence being shown in the image is almost a meta sentence from the book that says, decoding self-referential DNA, encoding these nodes. And we're able to just show how we take in this particular case, starting with the F in referential and ending in the N in DNA, take it to individual bits, which correspond to ASCII codes and a barcode, and then we take those ones and zeros and convert them to A, T, C, and G, or DNA bases, where T and G stand for 1 and A and C stand for 0. And so we just add PCR primers to the end of those and synthesize it. on a microfluidic chip. And so what's shown is the red barcode and the blue data block, essentially, that's in a larger context of other barcodes and data blocks. And then when we sequence the whole thing, and we'll get many copies of each particular barcode sequence. And then we're able to reconstruct the message, and then we just go back the same way that we encoded it, by decoding the message back to ones and zeros and then back to text. And because we have the address, we know where it goes back, so once we sequence everything, we're able to reconstruct what the original message that you're encoding or digital information that you were encoding in there.
This process might sound complex, but the potential is revolutionary. DNA storage is durable, sustainable, and extremely compact, making it perfect for long-term data archiving. Benefits of DNA data storage. DNA data storage offers several key advantages. Benefit 1. Unmatched storage density. DNA is incredibly efficient in terms of space. Imagine being able to store entire libraries or even the world's digital content in a space smaller than a sugar cube. Benefit 2. Longevity and durability. DNA is a resilient molecule. Under the right conditions, it can last for thousands of years without degrading, far beyond the lifespan of any traditional storage device. Benefit 3. Sustainability. Once encoded, DNA doesn't need electricity to store data, making it a greener solution compared to energy-hungry data centers. Benefit 4. Portability. DNA's small size makes it easy to transport. Instead of massive data servers, we could carry the equivalent of the entire internet in something no larger than a penny. Despite its promise, DNA data storage isn't without challenges. Challenge 1. Cost. At present, synthesizing and sequencing DNA is extremely expensive. Although costs are dropping as technology advances, it's still more costly than traditional storage methods. Challenge 2. Speed. DNA data storage isn't as fast as conventional storage devices when it comes to data retrieval. Researchers are working on improving the speed, but it's not yet ready for real-time use. Challenge 3. Error rates. Though error-correcting algorithms are improving, sequencing errors can still occur, especially with large datasets. This remains an area of active research. Challenge 4. Scalability. To make DNA storage a mainstream solution, we'll need more advanced infrastructure, from automated DNA synthesis to more efficient sequencing technologies. Applications of DNA data storage. Despite these challenges, the applications of DNA data storage are mind-boggling. Application 1. Archival storage. For institutions like libraries, museums, and governments, DNA could become the gold standard for long-term data preservation. Application 2. Data security. The process of encoding and decoding data in DNA offers a new layer of security. Data stored in DNA isn't easily accessible without specialized equipment, making it more secure against cyber attacks. Application 3. Space exploration. DNA's durability makes it ideal for storing data in extreme conditions, such as deep space missions where traditional storage devices would fail. As George Church, a pioneer in genetics, once said, DNA is the ultimate storage medium. Church and his team at Harvard have already made significant strides in storing digital data in DNA, paving the way for future development.
There are a few things where we may or may not admit it, but they're limited by our storage capabilities. So for example, if we could store everything, we wouldn't be throwing out data. We wouldn't be writing on top of reusing disks and tape drives. If we could store, say, video information over a broad set of the Earth, and then just store it, archive it, until something really good or really bad has occurred in that and then scrape the data and find out what actually happened in great detail. That's something we wouldn't even consider doing today, but you can imagine very inexpensive biological cameras that could encode it into DNA, and you could have very exhaustive archives of this that would only infrequently be accessed. Or you could imagine other huge data sources like all the neuronal firings in the brain, which could be encoded into DNA, and again, you could do selective reading of that as needed, and so on.
The future of DNA data storage is promising. As biotechnology continues to evolve, costs will fall and the speed of sequencing will increase. Soon, we may be using DNA to store everything from family photos to entire archives of human knowledge. In the long term, this technology could replace traditional data centers entirely, reducing energy consumption and enabling more sustainable digital infrastructure. DNA data storage represents a paradigm shift in how we think about data. It's compact, durable, sustainable, and secure, everything we need to manage the vast amounts of information generated every day. So, will DNA storage be the future of data management? It certainly looks like it. And as we continue to push the boundaries of science and technology, we may be storing the story of humanity in the very molecules that define life itself. Thank you for joining us on this important discussion. If you found this video insightful, don't forget to like, comment, and subscribe to Digi.AI.Velocity for more in-depth explorations of AI and technology. Until next time, stay informed and stay curious.